Hello everyone, my name is Fang. I'm a geophysicist and interested in developing geophysical tools to solve problems in cities. Traffic is one of the most important issues urban people need to face almost every day. Using camera, we can identify the vehicles, monitoring traffic jams, and even measure their speed. Only if we have cameras. For the case without image, can we identify traffic events? Please close your eyes and listen to the following audio. Well, hopefully you have identified that it's the sound of an aircraft flying by. Actually, ears give us more information than we expect. Geophysicists use seismic sensor, which we call it geophone, to listen the Earth. In this short video, I would like to show some new observations on traffic and aircraft-induced seismic signals. This research is in collaboration with my supervisor, Dr. Yunyue Elita and Dr. Ohad Barak. At the end of the last year, we implemented a joint geophone and smartphone experiment at NUS campus. We deployed 12 three-component geophones along a campus road. Their locations are denoted by these green dots. Three-component geophone means the geophone can measure vibrations of the Earth in 3 directions at once. In this case, Z component is set vertically to the ground. N component is parallel to the road. E component is perpendicular to the road. We record 15 minutes data with 1 millisecond time sampling interval and 10 meters spatial interval. At the same time, we have 7 people standing next to the geophones, holding smartphones and recording videos. These geophones and smartphones form an observation array. During our experiment, a civil aircraft fly over our array. The flight direction is indicated by the blue arrow. Now, let's first see what we have recorded at the station 6. On the top left panel is a piece of video recorded by the smartphone. We extract the audio from the video and plot audio's waveform in the bottom panel. Let's watch the video. So these large amplitudes come from the wind. There is signals from a bike and signals from a car. We have signals from a car going in the opposite direction. Signals from another car. Signals from a car and from a truck. Finally, we heard the aircraft flying over. On the right panel, we compare the 3 components of seismic responses with the audios on the same events. We can see all these 3 seismic components show higher signal-to-noise ratio on ground-based traffic. However, from seismic waveform, we can hardly identify the signals from the aircraft. Now, Let's move the time window to the aircraft part. These waveforms of the audio and the 3 seismic components contain 3 events of ground-based traffic and 1 event of aircraft. We applied short-time Fourier transform to each waveform and generate their spectrograms. The spectrogram has vertical axis of frequency and horizontal axis of time. Its amplitude indicates power spectral density, which is plotted in dB. If we focus on the ground-based traffic signals, the spectrogram of geophone recordings provide better temporal resolution and higher signal-to-noise ratio than the audio's. To our surprise, the aircraft signals, which seems to be undistinguished in the time domain, is clearly visible on the power spectrograms of all the 3 seismic components. We can identify 3-order harmonics of aircraft. Affected by the Doppler effect, the received harmonics shift from the high frequency to the low frequency. Since the aircraft was flying at an altitude of several hundred meters, the sound wave mostly impacts vertically. Consequently, the ground motion is stronger in the vertical component than the horizontal components. Compared with one single station, a station array can provide more spatial information for us. When we plot these audio recordings one by one, we will have a 2D audio profile, so as the seismic recordings. Based on the video information, we know that the large amplitude events that occur simultaneously in the audio and seismic recordings are mainly caused by moving ground-based vehicles. In general, the audio recordings show better spatial coherence than the smartphone audio data. Next, we zoom into a small piece of window and filter the data into a narrow frequency band, which is 25 to 70 Hz. We convert the vertical axis to the distance. There are 3 cars past our array during this time window. In the profile, we observed 3 groups of energy moving along the array. Using the travel time and the distance, we can estimate the average car speed, which is 36 km/h. In next part, we focus on the aircraft signals. This profile shows the aircraft-induced ground motion recorded by seismic Z component. We can see a group of energy from aircraft propagators along the array. Taking this channel as master channel and applying cross-correlation between this one and other ones, we can get the cross-correlogram on the right panel. By linear fitting the arrival time of the aircraft's main energy, we can get its apparent velocity along the seismic array, which is 1,308 meters per second. It is very large because of the angle effect. The Doppler effect is used in some types of radar to measure the velocity of detected objects. Now, I will show how to use the Doppler effect to obtain the flight parameters of aircraft with seismic data. From this formula, we know that there is a frequency shift between the observed frequency f and the emitted frequency f0. This frequency shift is determined by the velocity of the aircraft and the angle of alpha. Here, alpha is defined by the angle between the vector of the velocity and the line between the aircraft and the geophone. Let's first consider a case when alpha equal to 0. This means we observe on the trajectory line of the aircraft. This figure shows observed frequency along the time from aircraft moving in a constant velocity. When the aircraft is coming towards us, its velocity is positive. We will observe a high constant frequency. When the aircraft moving to the point of the receiver, the observed frequency will jump to the emitted frequency. When the aircraft going away from us, the observed frequency will jump to a low frequency. When there is an offset between the trajectory line and the geophone, the angle alpha will not be zero. In this case, the observed frequency changed smoothly. When we increase the offset, the curve is going to get smoother. Let's consider a more realistic situation. In this 3D case, the seismic array is deployed on the ground of surface, X or Y plane. The aircraft is flying at a certain altitude and at a constant velocity away. The angle between the projection of its flight direction on the ground and the seismic array is theta. For a certain geophone, the angle of alpha is in the plane defined by the geophone and the flight line. D is the distance between the aircraft and the geophone. D and alpha change with time. By defining flight distance S and the closest distance between the geophone and the flight line H, we have this formula, where all these unknowns are constants. Using nonlinear co-fitting, we can fit the Doppler effect observed in seismic data with this formula and estimate these unknowns. The estimated values are listed in this table. With aircraft velocity v and the apparent velocity, which is calculated by cross-correlation, we can further calculate flight direction theta. I want to emphasize that the first 4 parameters here can be obtained with only one geophone. After consulting a professional pilot, we believe that these obtained flight parameters are within a reasonable range. To the best of our knowledge, this is the first practical example of using seismic data to estimate flight parameters of aircraft. As conclusions, in this research, we demonstrate that geophone can record the ground motions induced by ground-based traffic and aircraft. We can use geophysical methods to extract many useful traffic parameters. These parameters describe the traffic situation or flight status. Our research reveals the potential new applications of geophysical tools for traffic monitoring and aircraft tracking. Okay, this is the end of my video. Thanks for your watching. If you want to know more about our research, please visit our website and feel free to contact us. Bye bye.